The next area that we're looking at for topic 3.1 is about projectile motion. You can see the two dot points there that we'll be referring to in this video. Now, projectile motion is a particular type of motion that we need to clarify. So we can consider it as being the motion of an object, and that object, consider it to have been launched or propelled. So it's not just sort of something moving along the ground. So it's been launched or propelled, and that's happened through a uniform gravitational field. Now, that idea of a uniform gravitational field we will come back to in a later area of topic 3.1, but I'll just mention it here now, considering that it is an important idea. That means that if it's launched through a uniform gravitational field, there's only one force acting on it, and that would be its weight. So only one force. That means that the force that's caused it to be launched or propelled, that's no longer applied. So we're not dealing with what's happening as you're throwing it, or as you're shooting something out of a gun, or hitting an object. We're dealing with what's happened after that force has been applied, and it's now moving through the air, and no other forces acting on it. Now, to make it a bit clearer, this idea of a uniform gravitational field, to simplify it a little bit, just consider that to be on Earth's surface. And the reason why that, just adding that there for clarity, just makes it a little bit easier to identify. And by saying on Earth's surface, we're saying that it's not in orbit, it's not in space where there's little or no gravity. We're basically just saying that we're only going to be dealing with the Earth's surface itself. Now, some examples of that, just to make it a little bit clearer, some sort of situations that you'd be familiar with would be things like the flight of a golf ball. So that could be considered projectile motion. A second one would be throwing a rock off a cliff. And the last one that I'll jot down here, say the arc of a three-point shot in basketball. So there's some scenarios that you can think about to help clarify situations where projectile motion is at play. Now, another point to note here, when we're dealing with projectile motion, we're not going to worry about the effect of air resistance. That's something that can be done. It's a little bit beyond the scope of this course, and it's explicitly stated in the syllabus that we don't need to cover it. So just making that note here, the effects of air resistance will be ignored. Or another way to think of it, you can consider that the effect of air resistance is negligible. And that means that they're so small that they don't need to be worried about. In some cases that's obviously not true. So if you, say, kick a football into the wind, you'll notice the path of that football is very different to if there's no wind. So it does actually come into play if you want a more full and complete analysis of projectile motion, but for this course we don't need to worry about air resistance. Another thing that's really important to note here as well is the fact that weight acts vertically. That then means that there's actually going to be no horizontal forces. So as the object is moving through the air, no horizontal forces acting on it, and so the horizontal motion is going to sort of be effectively separate to the vertical motion. So this means that the horizontal and vertical components of the velocity are independent. And what we mean by independent is that they don't affect each other. So the acceleration in the vertical direction have no effect on the motion in the horizontal direction. So that means that we can simplify the analysis of projectile motion even further by considering the two motions separately, so the horizontal and the vertical. So if we extend that to then look at the motions in general, the horizontal and vertical motions can be treated separately. So we can apply equations of motion only in the vertical direction, and the same can be done for the horizontal direction as well. And so we'll have a look at that now in terms of the equations, and we'll develop some equations that are in the data booklet. If we look at a situation where we have a projectile that's moving with a certain initial velocity, so something that's been, say, thrown in the air, where it's moving through a gravitational field, so we need to be aware of the fact that acceleration due to gravity is going to be acting on this object. We would also need to know the direction that this object is being launched, so we'll use that angle theta measured above the horizontal. Now, angles of projection are usually stated from the horizontal, so an angle of elevation or an angle of depression, but if they're not, then you just need to be aware of that when you go through and resolve the vector. So in order to treat the vertical and horizontal motion separately, we'd obviously need to resolve that first of all into two components. So ux in the horizontal and uy in the vertical. Now, some sources, if you go looking elsewhere, you might find that as uh and uv. So just using h and v for horizontal and vertical. The syllabus we're working from uses x and y. Now, if we go back to the equations of motion that we saw in Unit 2, we'll just jot those down really quickly just to refresh your memory. So we had s equals ut plus half at squared. Note that I'm using the vector notation here just to really highlight that they are vectors that we're dealing with, not scalar quantities. The data booklet itself, though, only uses doesn't bother using the vector notation, so just be aware that when we're dealing with these equations, we're dealing with the vectors. So there's the three equations: v equals u plus at and v squared equals u squared plus 2as. Now we can apply each of those equations to this situation that we're dealing with of this projectile moving through the air. So we can break it up first of all into the vertical and horizontal components. So let's look vertically to begin with. First thing we need to do is to resolve that vector, as I said, into the components. So using trigonometry, as we saw with vectors in 2 dimensions, we could identify that uy is going to be equal to u sine theta. That means that we can then change all of these equations into specifically projectile motion equations. So the first one then would be sy, and I'm going to reorder this just to match the data booklet. So if we take this half at squared term, instead of a, we're going to be writing the acceleration in the vertical direction being g. So I should actually make that note over here as well. So ay is actually going to be equal to g. So half gt squared plus uy t. So there's the first equation that looks like that. The second one, pretty straightforward, is just vy, and again reordering it to match the data booklet, would be gt plus uy. So there's the second one that's in the data booklet, and finally the bottom one there, again just adding the subscripts basically. Vy squared is equal to 2g sy plus uy squared. So there's the three in the vertical direction that we need to be concerned about. Now if we look in the horizontal direction, things are a little bit easier, and that's because horizontally we've got that we need to resolve again the initial velocity into the x direction, and so that's just going to be u cos theta. And in the horizontal direction, ax is equal to 0. So there's no horizontal acceleration. That means things are a little bit easier if we look at these three equations, considering that in each of these we have terms that have a in them, and so we can simplify them to two equations, one of which is a little bit pointless, but we can say that Sx is going to be equal to uxt. So there's another one from the data booklet, and like I said, the last one's a little bit silly in just saying that Vx is equal to Ux, so not really an equation that's needed, but it is in the data booklet just to make you aware of that. So that shows that the horizontal velocity of the object doesn't change throughout its motion. One last little point to make here. When you're dealing with projectile motion, we're resolving into components, but if the final velocity is required, so if we need to figure out what the velocity is when the object, say, hits the ground, that means that we need to sort of go in reverse and combine those two components back into one. Now, it won't always be required. It will depend on the question that's being asked as to whether you need to calculate the final velocity. So be guided by what the question is actually asking. But ultimately, the components Vx and Vy, you just need to add them as vectors. So that same process that we've seen already, so adding them vectorially. So the final velocity v is just the sum of the velocity Vx and Vy. Now if we consider what that would look like graphically, so again, if we have this projectile that's now moving this way after it's travelled through the air for some distance, so that would be our final vector v. We would then have to consider the fact that there would be a horizontal component in that direction and a vertical component in that direction, so that's Vy and that's Vx, and there would be an angle in here as well. We'll call that one phi, just to keep it separate from the initial. And so we could say there that as we've seen already with adding vectors together, particularly when they're perpendicular, we could then just say that that's going to be the square root of the magnitude of those two components, Vx squared plus Vy squared. So just applying Pythagoras' theorem, and we can figure out that that angle would be inverse tan of Vy over Vx. So similar to what we've seen already with vectors in 2D. One last point that's important to note, while the horizontal and vertical components are independent, they are still linked. And hopefully you can see by those equations that we dealt with earlier, the quantity that links them is the time. So we can take the time of flight in the vertical direction and apply it to the horizontal direction to get the how far it's moved horizontally. So they are still linked by time, and so that will be the way that we can figure out exactly how far or how high or how fast something is travelling based on how long it's been in the air, or what duration it's been in the air. Now in the next video we'll start to look at some applications of these situations and some special cases, and then we'll take that a step further as we continue to move through projectile motion.